we continue from last time on counting the number of maximal sum-free sets in the first n integers, bracket n. So as usual, this is the integers from 1 to n. Previously, it was known that there are 2 to the n over 4, meaning maximal sum-free sets. There are 2 different constructions. One by Cameron and Erdős in their original, when they raised the conjecture. The construction is easy. To construct this many maximal sum-free sets, always take the element n. Let's say n is divisible by 4. So there might be some error term here, but what we cared about is this power. Now, after always taking n, this element n pair up all the odd numbers into n over 4 number of pairs, because now we cannot take both elements from this matching edge. Otherwise, we get a shear triple. 1 plus n minus 1 is n. So we have to choose exactly 1 from these n over 4 pairs of odds, which give us this many choices. The other construction, similar in spirit, instead of taking n, we take n over 4 to pair up the third and the fourth quarter of the intervals. All right. After a sequence of work, finally, about 10 years ago, this is joint work with Yusuf Balog, myself, Marian Charizodeh, and Andrew Tracklon. We nailed down the exponents, showing that this n over 4 in the lower bound construction is the best possible. You cannot improve this 1/4 number further. So what we prove is this bound. And as I remarked last time, there is an even finer counting result where we remove this exponential error, we get a asymptotic counting. We can have some constant times plus some error term times 2 to the n over 4. So let's prove this weaker bound. Any questions? Let's prove this weaker bound. The idea is the starting point is a container theorem. So the idea, let me just briefly mention, is again, we start with a container theorem for sum-free sets. And this helps us to reduce the problem into bounding the number of maximal sum-free sets in an almost sum-free set in the container, which is an almost sum-free set. And then we will introduce some Cayley graph, some sort of Cayley graph, to translate this second problem here into bounding the number of maximal independent sets in some Cayley graph. Then we reduce it into bounding the number of maximal independent sets in certain Cayley graph. Okay. And for this, we need to prove several various, depends on the container. We need to prove various structures of the Cayley graph to utilize different type of bounds on number of maximal independent sets. So let's start with the first step of the reduction to reduce the problem into bounding maximal sum-free sets in certain almost sum-free sets. This container theorem for sum-free sets, we can obtain it from this hypergraph container theorem that I mentioned before, but the original form, the specific form for sum-free sets was originally proved by Green and Ruja. So let's start with the first tool, the container theorem. For some free sets. This is originally proved by Green and Ruja. Okay, so what did they prove? They proved that there exists a family of containers for some free sets. So there exists a family F, which is a subset of the first n integers, a collection of subset of first n integers, such that the following holds. First of all, it justifies the name for container. Every sum free set is a subset contained in one of these containers, which is a set in this family F. For any, let me just briefly write SF for sum free sets. So this is SF, shorthand. For every sum free set S, there exists a container F from F such that S is contained in this container. Okay. Second of all, there's not so many containers. Otherwise, just take all sum free sets. So the number of containers, which is the cardinality of this family, is 2 to the little o n. So we don't want to take too many. Third of all, every container, every one of these F, they are almost sum free. So for every F in F, almost sum free. What does it mean? The number of sure triple which is the triple x plus y equal to z, is little o of n squared. Why this is the degenerate case is in the set of size n, there are n squared choices to fix x and y. Once x and y is fixed, z is determined. So a positive fraction will be linear in n squared. So sublinear, subquadratic will be almost sum free. It's the small amount of short triple. The last one, it's obtained basically from the third one and some sort of removal lemma for short triple. And I would just write directly the consequence. So as a consequence of what I just said, every container in F, they have size not much bigger than n over 2, the maximum size. So for every F in F, the size of the container is at most n over 2 plus little o n. This is the container theorem. And at this point, after seeing the triangle free graph containers, seeing this again, every item you can correspond. Every item looks sort of standard now. The first item is always this is container containing the family that we cared about. In this case, some free sets. Second item is not many containers. Third item is every container almost has the same property as the family we cared about. For example, almost triangle free or almost sum free, or almost independent in the hypergraph container. And using this almost triangle free or sum free plus certain appropriate removal lemma, we can prove that every container is not much bigger than a genuine sum free or triangle free graph. Okay. Another tool we need is the a structural lemma, which is proved by Desui, Freeman, Schoch, and Temkin on large sum free sets, how they look like. You can view it as some sort of stability type of theorem for sum free sets, large sum free sets. So remember, when large sum free sets in 1 to n has size n over 2, there are two examples realizing this maximum size. One are all the odd numbers, 1, 3, 5 to n minus 1, dot, dot, dot. This has size n over 2, which is sum free. Another one is second half of the interval. So 1 to n, you take this part, n over 2 plus 1 to n. This is also sum free of size n over 2. Okay, these are the two examples. Now the next tool we need is some sort of stability, saying that when your set is sum free set is close to n over 2 size, 0.5 times n, then structurally you are close to one of these two examples. So this is lemma by Desui. So here's the statement. Combining with container, so this is not their original statement, but combining with removal lemma, we get the same statement for almost sum free sets. So here's the statement for every set subset A in N, which is almost sum free, with almost sum free means little o n squared number of shared triples. And what I know is the size of A is close to 1/2, is 1/2 minus gamma times n, where gamma could be a function of n, is strictly less than, is some constant, strictly less than 1 over 10. Then the conclusion is one of the following holds. Either in the first alternative, your set A, almost sum free set, it looks like the second half interval. So what it means is all but little o n elements of A are contained in the interval 1/2 minus gamma times n and n. This is, if you think about gamma to be 0, this is basically second half interval, right? If the second alternative is almost all elements of A are odd numbers. This is the second extreme example where you take all the odd numbers. A subtract all the odd numbers, let's say O is little o n. This is what it means. Okay. Now, there's a remark about this lemma, some sort of stability, is that this 1 over 10 is best possible. Remark. 1 over 10 is best possible. You cannot replace it by any constant larger than 1 over 10. When it's 1 over 10, what do you get here? 0.4 times n, 2n over 5, right? This is because if it's larger than 2n over 5, this is larger than 1 over 10, this is smaller than 2n over 5. You can take 1, 4 modular 5 or 2, 3 modular 5. These two examples in n both have size 2n over 5. And they are both sum-free sets. Simply because 2 plus 2 is 4, 3 plus 3 is 1, 2 plus 3 is 0 mod 5. So this is sum-free set. Similarly, this is also sum-free set. 2n over 5. And these two sets, just barely failing this hypothesis, does not look like any one of those two examples. It has tons of elements in the first one half, and it has tons of even elements. Okay? So I will not prove this lemma. We just use it as a black box. These are the two tools that we will need to do the first reduction step. And let's review the tools we need for the second reduction, for the second step when bounding maximal independent sets in certain KD graphs. We've talked about this last time. Let's quickly review all the statements. The first statement is upper bound on number of maximal independent sets in an n vertex graph. Okay. The first is Moon and Moser, which says for any graph, we have at most 3 to the n over 3. And then Huiter-Tuza showed that because of this disjoint union triangle, we cannot go beyond 3 to the n over 3. If it's triangle free, the graph, then we can improve it to 2 to the n over 2, which is again typed by perfect matching. We can do the hybrid version, which I leave as an exercise, showing that if exists some sets T of vertices such that G minus T with T vertices in T removed is triangle free, then this hybrid version says number of maximal independent sets in G is at most 2 to the n over 2 plus T over 2. Sort of hybrid version. Try to prove it using the first two. And the last one we covered last time is an improvement of this Moon and Moser. This when the average degree of the graph G is sufficiently large, we can improve. For example, if it's regular and sufficiently large, we can improve it to 3 to the n over 6. So what we want is for almost regular, sufficiently large density, the following lemma. So D sufficiently large, and the maximum degree is at most k times the minimum degree. And minimum degree is D, which is sufficiently large, Then we have number of maximum independent sets is at most, is at most 3 to the k over k plus 1 times n over 3 plus little o n. So this we proved it using a similar algorithm as Kleiman-Winston, an algorithm that's an idea of Shevchenko last time. So this is the tools we need for the second step. Now let's put things together and try to finish the proof. So what will be an ideal case? Ideally, in a beautiful world, we would like something like the following happens. Ideally, we know that here, let's look at the container. To count the maximum number of maximum sum-free sets, we know every sum-free set is contained in one of these containers. And the number of containers is 2 to the little o n. So 2 to the little o n is the error term. That means we just need to, we can forget about this and focus on one container. This is negligible. When you focus on a container by removal lemma for sum-free sets, we know the container, we know the container can be split into a genuine sum-free set and a set of size little o n, right? Because it's almost sum-free by removal lemma. So ideally, what we would like to do is fix a container now. We know that F equals to A union B, where this is sum-free, and this is little o n size. By removal lemma, we have this. Now, what we'd like to do in the ideal case is we want to bound the number of maximal sum-free sets in F, right? What we can do is two-step. In the first step, we choose how we can build a maximum sum-free set. We choose its intersection with B. We choose S in B, which is sum-free, to include in our maximal sum-free set. The number of these choices is 2 to the little o n, simply because B is tiny. Now we're going to extend S into a maximal sum-free set using elements in A. Through some, it's not hard to show that we can build some Cayley-like graph to translate this into this. It's not hard to show that it's the same as the number of maximal independent sets in some Cayley graph. Okay. And the order of this graph is size of A, which is n over 2, at most n over 2, because this is sum-free. So far, so good. But remember, the bound we need is bound we need is 2 to the n over 4 plus little o n. So in order to have the final bound, we would need to prove that this KD graph is triangle free. So you have 2 to the order of the auxiliary graph divided by 2. So KD graph gamma. So if gamma is triangle free, we are happy. We are done. But the thing is, as we shall see, in many cases, gamma is not triangle free. It even has many triangles. That's why we need all these different versions of ways of bounding maximum independent sets when the graph is not triangle free. This is not the case, unfortunately. So even though the last step is not as smooth as we would like, but all the previous step we can carry out as we anticipated. So let's write down the previous step in details. Any questions so far? So good. If there's no question, let's finish the first step of the reduction and try to define this KD graph gamma to reduce the problem into this second step, the number of extensions into maximal sum free sets into bounding the number of maximal independent sets in this KD graph gamma. Proof. Okay. So prove that number of maximal sum free sets in N is 2 to the N over 4 plus little o n. First step using container. So let F to be the family of containers for sum free sets in N. Then what do we know? We have this will imply this number, let me give you a name, is F max of N, say, right? So this F max of N, maximal sum free sets in N, is at most the cardinality, the number of containers in F times 2 to the, I don't want to do that, times max F in F A in F, the X F max of A. This is the number of maximal sum free sets of N in A. Okay. Every sum free set is containing one of these containers. So this obviously gives an upper bound. This is of size 2 to the little o n. Remember, 2 to the little o n, which is error term here. So it suffices to prove for any fixed any container, we can bound it, we can bound F max of A, the number of maximal sum free sets in A, by 2 to the n over 4 plus little o n. So it suffices to show for n in A, now let's fix one in F. The number of maximal sum free sets in A is at most 2 to the n over 4 plus little o n. Okay. Good. Now we divide into cases. We divide into 3 cases, 2 of which close to the extremal results for maximum sum free sets, the set of odd numbers or the second half of the interval, structurally when they're close to them. And the third case is when they're not very close to maximum sum free sets. Their size is bounded away from 0.5 times n. So let's consider 3 cases. This is by the structural results by lemma star. Okay. Lemma star is this lemma. We know that either the sum free sets, the almost sum free sets, we know every container satisfies this, right? By our container theorem, every container satisfies this. Either its size is bounded away from 1/2, or it looks like one of these 2 cases. Let's write it down. Either case 1 is that 3 cases. A satisfies one of the following. One is A is smaller than 1/2 minus let me take something strictly less than 1/10. Let me just take 1/11 for gamma, which is at most 0.45 times n. Or B, or for some gamma, which could be negative 1/11, at most 1/11, such that A is close to the second half of the interval. Close to the second half interval means the intersection of A with the first half of the interval is tiny. Or C, A is close to the odd number. Again, size is 1/2 minus some error gamma, and A minus the odd number is little o n. We have these 3 cases. Okay, now we're going to build our auxiliary graph, this Cayley graph. How do we build it? Well, we know Okay, before we build that, actually in 3 different cases, we're going to build our zero graph in 3 different ways. So before we do that, let's introduce a notion and a lemma to translate bounding this extension in of, you have this 2-step, right? You decompose this sum free set into 2 different sets, and we're gonna extend it. So the definition is, let's have given 2 sets B and S, which are subset of the first n integers. We define the link graph of S on B on vertex set B as follows, where let me call it LS bracket B. The vertex set of this graph, this is a graph defined on the vertex set B. For the edge sets, we have two types of edges. The first type is XY adjacent in B. XY elements in B adjacent if there exists Z in S such that XYZ is a shared triple. Okay. Cool. This is a very natural definition. Why? Suppose at the first stage, we choose already some element S into our maximal sum free sets. Now we're going to extend S into a maximal one by adding some elements from B. What's the restriction? You have B here. If you have XY, you add an edge. If there exists a Z such that XYZ form a shared triple, that just means that we cannot add both X and Y into the extension to S. Otherwise, we will get a shared triple. You are not a sum-free set anymore. So picking an extension is the same as picking an independent set in this auxiliary graph, link graph. And we will further see that if you want the extension to be maximal sum-free, this independent set you pick must also be a maximal sum independent set in B in this link graph. But there is for technicality, there is another type of edges, which is a loop vertex loop at X if either X, X, Z is a shared triple. So sometimes we also need to avoid this case for some Z. In S or X, Z, Z prime is a short triple for some Z, Z prime in S. This is kind of like just for the rigorous. It's not the main order term. You can, whenever it's a loop, you delete it automatically. It cannot be included into the extension. So mainly we focus on this one. Okay, after defining this link graph, we know that we will use the following lemma. It says that suppose both these two are sum-free sets themselves, then this link graph, the number of maximal independent sets in this link graph upper bounds the number of extensions of S into maximal sum-free sets in B union S. So for any sum-free sets S and B in N, can I change the reaction time of sensitivity? Is it low? Is better? Let me see. or high is better. I don't know which one. Rejection, probably high. Okay, for every sum free set B and S, if we choose this extension, meaning that we choose some subset of B to add it to S, is such that S union I is a maximal sum free set, then I is an maximal independent set. In LS of B. Okay. This proof is simple. I will leave it as exercise for you. Just try to digest this definition of the link graph. You should follow right away. Now, let's start with finding different decomposition of each type of containers and try to apply this lemma to reduce it to bounding maximal independent sets in different link graph. So the first type is the easiest one, the small container. So we have the three type here, remember? Small container, or a container that's like the second half of interval, or the container that's like the odd integers. Case one, small containers. Here's the lemma. For any A in the family of containers with size, in the small container, it has size at most 0.45 n. Okay, then the number of maximal independent sets containing A is a little o of 2 to the n over 4. So it's negligible amount. Proof. This is not hard. For this decomposition, we just use a removal lemma. So by removal lemma, I didn't write it down rigorously, but what it says, consequence is that since A, this container is almost sum-free, shear triple is subquadratic, so we can decompose A into B union C, where B is genuinely sum-free, and C is a set of size little o n. It's like a trash set. You remove some elements, then remaining sum-free. Now, every maximal sum-free set in N containing B, containing A, can be built in the following two steps. The first step is we choose some set, a sum-free set S in C, this trash set. Second step is extend S in B to a maximal one. Okay. The number of choice for the first step is at most 2 to the size of C. You choose subset of C, right? Which is 2 to the little m. So we don't care about this. It's tiny. What about the extension? The number of extension for fix S. You fix a S. The number of choice for S is tiny. Fix an S. Now S is sum free. B is also sum free, we can use this lemma. For two sum free set S and B, if you ever has an extension for S to a maximal sum free set, then such extension corresponds to a maximal independent set in the link graph. So by the lemma, implies that the number of extension for S is at most MIS of this link graph on B. This is a graph on vertex at B, which has size at most the size of A, which is not big. This is where we use small container of size 0.45. So we can use just the vanilla Moon and Moser. This is at most by Moon and Moser, 3 to the B over 3, which is much less than 2 to the 0.49 times n. So this is exponentially smaller than n over 4. We have 5. This is the easy case. In the remaining two cases, we're going to do the same, but we might decompose it in a different way, not necessarily using removal lemma. All right, let's look at the second case. When the container is close to the second half of interval, A is close to second half of interval. So this is the precise lemma. In this case, you have a gamma that's between at most 1 over 11. And what do you have? A is almost sum free. And A size is close to 1/2. And A is close to second half of the interval. Then we have F max of A is at most 2 to the n over 4 plus little o n. This lemma will finish the second case. How do we prove it? We don't use removal lemma to split A into a sum-free set and little o n negligible size sets. We cut A into by its intersection with the first half interval. So let A1 to be A intercept with the first half and A2 to be the remaining, which is A intersect the second half. What do we have? Because of this property, A intersect the first half except gamma n element is little o n. So A1 is at most gamma n plus little o n. Okay, A1 is not big. Now, we're gonna do as we did for the first case. We're gonna first choose some sum-free sets in A1 and extend it into a maximum one in A2. Now, we first choose S in A1, sum-free, and extend S to a maximum 1 in A2. That means what? The number of choice for this is at most 2 to the A1. Okay? And by the lemma, we know the number of choice for fixed S is at most the number of maximal independent sets in the line graph of S in B. Oh, well, B in this case is A2. Sorry. So this is A2. Good. Right. So now we need to prove some property. So this line graph. So let this graph to be G. So call this graph G. This graph G will prove that it's triangle free. Claim G is triangle free. Before proving this claim, let's see how it finishes the proof, right? So why it finishes the proof? If G is triangle free, then we have, this will imply that F max of A is at most the number of choice for the first step. Choose is intersecting with A1, 2 to the size of A1 times, now you fix the choice of S. We multiply this already. You extend it here. And the extension is MIS of G. But G is triangle free. So it's 2 to the A1 by Huiter to the triangle free means is the number of vertices in G, which is A2 divided by 2 times 2 to the A2 divided by 2. Okay. So we just need to see that A1 plus A2 divided by 2 is at most n over 4 plus little o n, then we are done. This is at most what? Let's look at the power. A1, we know it's at most gamma n plus little o n. How do I write it? This is A1 plus A2 is 1/2 minus gamma times n. This is the size of A minus A1, right? This whole thing divided by 2. This is A minus A1, you get A2. So what we have is this guy divided by 2 plus A2 divided by 2. So this equals to 1 quarter. Let me write it slowly. Yes. Okay, this equals to this n over 4 plus A1 minus gamma n divided by 2. Okay, you can check the calculation. Now we are done because A1, what do we know? A1 is at most gamma n plus little o n. So this is little o n at most. And we are done. So we just need to prove this. G is triangle free. Why is G triangle free? Okay, let's prove it. This is not hard. Let's draw some picture. This is the first half. Here is A1, its intersection with the first half. Here is A2, its intersection with the second half, right? Now, this line graph is on A2, so this is the vertex set. Suppose you have three elements, X, Y, Z, in increasing order. Suppose they form a triangle in the line graph. Suppose you have X, Y, Z forming a triangle. What does it mean, triangle? That means there exist some elements in A1 by definition for this XY. There exists some S1 that form a shear triple with XY. What's the only way that form a shear triple with XY? If you sum these two, the element will be out of N. So the only way to form a shear triple is this guy is the difference of XY. So Y minus X is some elements in A1. That's the only case, possibility. So we have similar for YZ and XY. There exist S1, S2, S3, such that, or ABC maybe easier. ABC, right? ABC in A1 such that Y minus X is A, Z minus Y is B, Z minus X is C. But then, if you add up these two, you get Z minus X is A plus B equal to C. This is a shear triple. In A1, which is a contradiction. Or in S, sorry, S is a sum free set in A1, okay? Any question for this step? The second case is also not too hard. The most complicated case is the last case when the set is closer to the odd integers. Let's look at the last case. Statement goes as follows. When A is closer to the odd numbers, lemma for any A in the family of containers such that most of its elements are odds, meaning A minus O is little n, then F max of A is at most 2 to the n over 4 plus little o n. This is the boundary we want. For this last case, we have to do some work. Proof. So what do we do? Well, take an A that's as in the hypothesis. Now, by enlarging the set A, if necessary, that will only increase F max. We may assume that A actually contains all the odd numbers in O. and then some little o n elements that are even, right? By adding all numbers, if necessary, which can only increase f max, the number of maximal sum free sets. When you add more elements to A, we may assume A actually consists of all the odd numbers union some set of even numbers. So this is a little o n size, and C is a subset of even numbers, E. Okay. Now we're going to use this decomposition. We first find some set S in C, and then extend S in odd numbers to a maximal sum free set. So to bound the F max in A, choose S in C, extend S in O. The number of this choice is again 2 to the C, which is 2 to the little o n, negligible. So you just need to show this number, which by the lemma is MIS of LS of B. Well, B is O now. This is at most 2 to the n over 4 plus little o n. This is what we need to prove. Okay. We're going to prove these in two different cases, depending on the size of this set S, this generating set of the Cayley graph, this link graph LS of O. In the first case, we have S is sufficiently large. It grows with the underlying set N. We don't need it to be N to the 1 over 4. You just need it to be sufficiently large constant. Let's say it's at least N to the 1/4. Okay, in this case, we're going to show that G, this link graph, let's call it G, is dense and almost regular. It's not too sparse. And almost regular. If this is the case, what we do is we can use this result. Not too sparse means its minimum degree is sufficiently large. This is why we take the generating set S grows with N, so that the size of generating sets directly link to the minimum degree of this link graph. We need to prove that it's almost regular. Then we can use this improved bound. If you just use Moon and Moser, it's not enough. We need to use this improved bound to get the desired result. Okay, so let's do that. Here's what we need to prove. First of all, the minimum degree of G is at least S over 2. So this is sufficiently large because S is at least n over 2. And we will show that the maximum degree is at most 2s plus some constant. This will imply what? For example, in particular, delta s is at most 6 times delta of g. For example, this is 4 times, s is at least 1, so this is another 2 times. So this is at most 6 times. Actually, you can even put 4 plus epsilon here, but 6 is enough. Now you use the lemma with k equal to 6 before. Suppose this is true. This would imply that MIS of G is at most 3 to the k equal to 6. So k over k plus 1 is 6 over 7 times the number of vertices in G is O, which is size n over 2. Number of vertices divided by 3, remember, plus little o n. And this is at most 2 to the 0.24 n, which is negligible, little o of 2 to the n over 4. So this case, we can also forget about it. And why is this true? I just hand wave the proof. The proof is not hard. So this is because when you fix the arbitrary element of the vertex, arbitrary vertex in this graph, which is the odd number, fix the odd number. X. Okay. Now, for any element S in S, which is a subset of the even number, this S, it's not hard to see that either S plus X or S minus X or X, let's say S is less than X. If you pick it from the left, then X minus S, they are both odd number, right? Just pick this one, X minus S. It's another odd number. So this S contribute to an edge between X and X minus S, right? Let me briefly write it here. For any X which is odd, and for any S, if S is less than X, then S contribute to this edge, right? If S is bigger than X, even number, then it contribute to this edge, S minus X, right? So every S, whether it's bigger than S, every even number, whether it's bigger than X or smaller than X, contribute to an edge incident to X in this link graph. And the edge we divide it by 2 is because an edge could be caused by 2 different S and S prime, because of this S minus X or X plus X business. That's it. For the maximum degree is similar. I will leave it as exercise. I'll skip the proof. Any question for this step? Then we arrive to the last case, which is the troublesome case when the generating set is not growing, let's say less than equal to n to the 1 over 4. What we need to do in this case is we should prove that this link graph G has little o n triangles sublinear number of triangles in total. If this is true, we're going to let T be the vertex set of all triangles. What do we have? G minus T is triangle free. And remember this bound, this will imply that MIS of G is M most 2 to the N over number of vertices in G over 2 plus number of vertices in T over 2, remember? And number of vertices is number of odds, which is N over 2. This is 2 to the N over 4 plus little o n. Oops. Because T is at most 3 times the number of triangles. You take all the endpoints. So it's again little o n. This will finish the proof if we can prove this. So this is the claim. Right? Now let's prove this claim. To prove this claim, we have to be careful how triangles are generated in this. There could be triangles, but we have to show that certain triangle, it does not show up. Otherwise, there could be many, many triangles. So what we need to show is, so let me illustrate what I mean. We don't want a triangle that look like this. Need to show no such triangles. So this is a bad triangle. The vertex set of this graph are odd numbers. So for example, the endpoint of triangle is 1, 3, 7. So what are the generating sets? That means there is an element 2 in S. 1 plus 2 is 3. 3 plus 4 is 7. 1 plus 6 is 7. So the element 2, 4, 6 will generate this triangle in G. Okay, this is impossible actually because 2 plus 4 is 6. This is the impossible case. But in this impossible case, this is bad because we can translate this triangle to get many, many triangles. So you can translate it to say 9, 11, 13. This is again 2, 4, 6, right? Dot, dot, dot. By translating, you will get little linear in M many triangles. But in this particular example, we know 2 plus 4 is 6. It's impossible. We will show that all such bad case that will generate many triangles are impossible triangles to appear in our big graph. All the other triangles, they can only have little o n's many. Okay, so to do that, we need to classify the edges in the link graph. So for every edge, x, y, in G, we know that either in the link graph, we know that either x minus y is the generating element, let's say little s, in S is the generating set. Either x plus minus y is S, or the absolute value of these. Well, I don't know which one is bigger, or their sum, x plus y, is S in S. That's how we get this edge x, y in the link graph. One of these two cases. Let's call the first case, let's color these edges in the link graph blue if it's the first case. So and red otherwise. Otherwise means this. Otherwise means this is not in S and x plus y is in S. Okay. So what is this type of triangle? For example, this kind of bad triangle corresponds to anyone? This is x minus y is in S, right? This is all minus. This should be 15. All minus, so they are all blue. This is all blue triangles. This is blue, 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 blue. So the next claim says all blue triangle is impossible. Neither is the triangle with exactly one blue edge. Claim each triangle in G has either 0 or 2 blue edges. It cannot have 3. It cannot have 1 either. 1 is bad because you can do this translation again to get linear in n number of triangles. So in both those two bad cases, you can get linearly many. So let's prove this. The proof is simple. Suppose XYZ is a triangle in G. And suppose it has exactly the all blue case is here. I will leave it for you to prove it. All blue case corresponds to 3 generating elements. 2 plus 4 equal to 6 from a sure triple in S. But we know S is sum free. That's a contradiction. So let's prove the case has exactly one blue edge and try to get a contradiction. In this case, let's assume, let's say S1 is Z minus X and S2 is X plus Y. This is red. This first one is blue. And S3 is Y plus Z, right? In this case, S1 plus S2, S3, contradicting to S being sum free. Okay, so it's impossible. The other cases are similar. I will skip it. Good. So if every triangle has, in G, has either 0 or 2 blue edges. Now for the rest, we just say we only have 2 types of triangles. Either you have, so we have for any triangle, you have 1, 0 blue edges. That means you have 3 red edges. So either it looks like this, or 2 blue edges. That means you have 1 red edge, or you look like this. Okay, this is the only 2 cases. We're going to show that in these 2 cases, the number of triangles is little n. So we only have, by the above claim, for any triangle, x less than y less than z in G, we are one of these cases, right? So either these are 4 cases. Either all edges are red, or exactly one edge is red. So this one edge could be XY, could be YZ, could be XY is the only edge, only red edge. Or YZ or XZ is the only red edge. Okay, these 4 cases. I'll just prove one of these cases, and the other cases are similar. Let's look at the first case. Okay. Every triangle, in the first case, you have a triangle that look like this. X, Y, Z. First case, all red. All red means what? Red means their sum is an element in S. So that means you have S1, YZ is S2, S3, right? X plus Y is S1, Y plus Z is S2, X plus Z is S3. This is the first case. The other case are similar, all right? For the first case, okay, we're going to argue that for any such triple, S1, S2, S3, it can only create 6 different triangles, red triangles like this. Okay. For any S1, S2, S3, in S cross S cross S, in a generating set, can create at most 24 red triangles. In G. If this is true, what do you imply? It will imply that the number of triangles of type 1 is at most 24 times S cubed. But what do we know about S? It's at most n to the 1/4, so it's little o n. N to the 3/4, which is little o n triangles, as needed. For type 2, 3, 4, they are all similar. You just need to prove at most 24 triangles for each fixed triple. This is the last thing we have to prove. For fixed triple, you can create such red triangle in at most 24 different ways. No, 6 different ways, all right? You can prove even better. Okay. If it force if S1, 2, 3 force such a red triangle, that means what? That means this linear system of linear equation, this corresponds to the all red. This is a vector, all right? S is a vector. Has a solution. Right? Because this is basically this guy. X plus Y is some elements in S, which is S1, 2, 3, where S contains, is a vector contains S1, S2, S3. It's a permutation of these. This determinant is non-zero. It has a unique solution S. And by permuting S1 to 3, you get 6 different permutations. That's it. Any question? Just to give you some why this case is bad in this matrix form, this is all blue, 0 red edges, right? If 0 red edges, that actually correspond to, so all blue triangle correspond to the matrix -1, 1, 0, 0, -1, 1, -1, 0, 1. This has determinant 0. So there are infinite many solutions it could be. So is the other case, the 2 red edges. Is the determinant, is the matrix that look like this, which also has determinant 0. That's the 2 forbidden one that could generate many triangles, which we excluded by this simple claim here. All right, any question? So once again, the last step, we want to prove the other cases are similar. There are little o n number of red triangles, all red edges. Each such triangle is created by some triple S1, 2, 3. And the number of triple is S cubed trivially, which is little o n. We just need to show for every triple S1, S2, S3, by permuting it, if necessary, you get at most 6 different vectors S with entries S1, 2, 3. If you ever have a red triangle, this vector, after permuting, it's a solution to this system of linear equation by definition. And since this determinant is non-zero, there's a unique S up to permutation, which finishes the proof. Okay. All right, if there's no question, we're going to continue on Thursday. See you guys next time.